everyone, my name's Annabelle. I'm a fifth year student doing physics and renewable energy engineering. I'm going to be doing question 3 and question 5 from the Physics 1A final exam from term 3 2019.
Let's start with question 3.
It's about the moment of inertia of a rod with a non-uniform density. Part 1 is what is the mass of the rod. So I've redrawn the diagram from the question here. This is the sort of question that we do with an integration. So the first thing to do is break up the rod into little slices of mass dm. We have dm equals linear density times length, so lambda dx. Then the mass of the whole thing is just to integrate dm along the rod. We sub in dm equals lambda dx. Use x equals 0 to x equals L for the limits, and then we just substitute in the expression for the density. I don't really like the way they've done the units on this expression. X is already a length, it's already got units, so you shouldn't be able to just slap a different unit on it, but this is an exam, so we're just going to roll with it. This is an easy integral. You sub in L at the end and you get an answer of 6 kilograms. The written solutions kind of look like they say 4 kilograms, but from this line I'm pretty sure it's 6. Part 2 is find the moment of inertia of the rod. So our usual formula for that is the integral of r squared dm over the object.
R squared in the formula
is the distance from the pivot point. The pivot point is marked in the diagram, and the distance from it is defined as x. So we can just use x squared, and as in part 1, dm equals lambda dx. Sub in lambda, do the integral, we sub in L, we wind up with 10.7 kilogram meters squared, where you can write it as meters squared kilograms if you prefer. I've rounded this to 3 significant figures because that's the precision to which the question gives its numbers. But for later parts, it's also handy to have the exact form, which is an improper fraction in this case. Now, part 3, we're going to imagine this rod spinning about the same pivot on a frictionless horizontal table, with a force of 5 newtons applied perpendicularly to the end of the rod furthest from the pivot point. Just based on the way they've drawn the force here, we're going to sort of imagine that the page is the table, so the rod will start spinning sort of anti-clockwise over the page as I've kind of drawn here. We need to find the angular acceleration, but before that we need the torque. Formula for torque is r cross f, where r is the vector from the pivot point to the point where the force is applied, and f is the force. So the angle between them in this case is 90 degrees, so that sine theta goes away. It's just the product of the magnitudes. The direction of the torque we can find by the right hand rule. So we go in the direction of r, direction of f, and your thumb should end up pointing out of the page. That corresponds to if you curl your fingers in the anti-clockwise direction that it's spinning, your thumb goes out of the page. But the direction's not super important for this question. So we just do length of r, which is the same as L, the length of the rod, 2 meters times the force 5 newtons, we get 10.0 newton meters, again to 3 significant figures. Then to get the angular acceleration, we use the rotational version of Newton's second law. Torque equals moment of inertia times angular acceleration. We rearrange, we sub in our numbers. This is where I use that improper fraction. And our final answer rounds to 0.938 radians per second squared to 3 significant figures. We know that angular acceleration should be in radians per second squared, but just over here I've checked that the units we substituted in do actually come out to that. Radians is a unit that doesn't have a dimension, so you are allowed to just stick it in when you know conceptually that it should be there. So question 4 is going to be done in a different video. We're going to move on to question 5 for now. This one is about waves and simple harmonic motion. So it says a tennis ball of mass m is attached to a 1 meter string of negligible mass. That's a hint that this is a simple pendulum. The tennis ball is moved by 10 degrees from its equilibrium position and at time t equals 0, released from rest. The movement of the tennis ball can be approximated as simple harmonic motion. Parts 1 and 2 calculate the angular frequency and the period for this oscillating system. I did the period first because that's the formula that I could remember. T equals 2 pi square root L over G. That's just plug in the numbers, round to 3 significant figures. This A is something I put to note that I saved that in the calculator, which you can do if you like, but it's not essential. Then I went back to do part 1 and calculated the angular frequency from the period. You can do parts of questions in whatever order you want, as long as they don't say hence or using the previous part. The angular frequency comes out to 3.13 radians per second. Okay, then on to part 3. So they give you this sine curve shape and you sort of just have to add in the axes and the labelled values. What you need to label is the amplitude of the oscillation. That comes from the initial displacement of the tennis ball up here. And also the period that we worked out in part 2. So that's the time taken for the tennis ball to go through one whole cycle. Then in parts 4 and 5, we need to indicate on the graph all places where the speed of the tennis ball is largest and where it's 0, then the places where the different kinds of energy have maximum and minimum values. That's sort of 2 ways of saying the same thing. So when the speed is largest, the kinetic energy is maximum and the potential energy is minimum. When the speed is 0, the kinetic energy is 0 or minimum and the potential energy is maximum. So you could just label the graph if you wanted, but I thought it would be clearer to have a sort of legend here. So crosses for the high speed, high kinetic energy locations and dots for the 0 speed, highest potential energy locations. Those are respectively at the intercepts of the graph. So this is where the tennis ball swings past the center and it's going fastest. And the peaks and troughs are where the tennis ball reaches maximum displacement and stops for a second. A loudspeaker is driven by an oscillator whose frequency can be varied. The speaker is placed at the end of a 1 meter long open pipe and its frequency is increased from near 0 until the first resonance is heard. Assume that the speed of sound is 330 meters per second. Part 1. Draw a diagram to illustrate where along the pipe are the maxima of displacement amplitude are found. That sentence is a bit weird, but we get what they mean. This is a question about standing waves. Standing sound waves to be precise. This is my diagram. So I put loudspeaker at one end, both ends of the pipe are open. Open ends form displacement antinodes because the air molecules are free to move wherever they want. So that corresponds to the peaks and troughs or the maxima of the displacement wave. So because we increase the frequency from 0 to the first resonance, this is the longest wavelength standing wave that can fit. It's where the length of the pipe is half a wavelength. Part 2 is actually sort of easier. It asks the same thing but for the pressure maxima. So pressure nodes correspond to displacement antinodes. Or another way to look at that is that the pressure is pretty much at constant atmospheric pressure at the ends of an open pipe. So that's where you put the nodes of the wave, and it's kind of easier to see that this is a half wavelength and it's a stable standing wave. So to answer the question, point of maximum pressure variation is in the middle of the pipe. Part 3, at what frequency does this first resonance occur? So for this, we use what I just said a minute ago, which is that the length of the pipe forms half a wavelength. That's just, so make lambda the subject, we'll use the speed equals frequency times wavelength equation. I know this is sound, not light, but I've used c for the speed anyway. So then we just rearrange for f, substitute in what we had for lambda, substitute in the numbers, and we should end up with 165 hertz. Now part C is about the Doppler effect. So the source of sound is a bat, the observer is you. The bat is moving towards you at 8 meters per second and emitting sound at a frequency of 50 kilohertz. So the form of the equation that we would use is something like this. So the observed frequency is equal to the source frequency times this factor of, so c, the speed of sound, c over c minus velocity of the source. It's minus because the source is moving towards the observer, so you want the frequency to get bigger. If you plug in all the numbers, it comes up with 51.2 kilohertz, so a bit bigger than 50. Part 2 asks what is the beat frequency from the sound reflected from you back to the bat and the sound emitted by the bat. Of course, I didn't read this closely enough the first time, so I just tried to subtract these two, but that is not the right answer. You have to think that the sound reflects off you, so you become the source, and the bat becomes the observer. But then the bat is still moving towards you, so the sound gets Doppler shifted again. In other words, our source frequency is now 51.2 kilohertz that we just worked out in part 1. The source is you are not moving. The observer is the bat, and that is moving at 8 meters per second towards the source. So our formula looks a bit different. The observer velocity goes in the numerator, which is different to how earlier we put the source velocity in the denominator. But they're moving towards each other, so we still want the frequency to get bigger, so this is a plus. Which means that the bat hears the sound coming back at 52.5 kilohertz, and then to get the beat frequency we can just subtract them to get an answer of 2.5 kilohertz. Now in part D, so you have two masses on vertical springs. You pull them both down, but one by 10 centimeters and one by 20 centimeters. If you let them go at the same time, which mass reaches its equilibrium position first? So for this we need either the angular frequency or the period of the motion of a mass on a spring. Whichever way you prefer to think of it, they only depend on m and k. They don't depend on the initial displacement or the amplitude of the oscillation. So then if you think of when the mass springs back to its equilibrium position, you can think of that as the first quarter of a cycle of simple harmonic motion. It takes a quarter of a period, and since the period doesn't depend on the amplitude, they will both reach the equilibrium position at the same time. Another thing to see here is that obviously the mass that you pull down by 20 centimeters has further to go to get back, but the initial force on it is larger because of Hooke's law, F equals negative kx. So it will experience a greater acceleration, and this cancels out the extra distance, so they end up taking the same amount of time. So last question, question 5, part E. The string of a guitar with fundamental frequency 256 Hz is plucked while two tuning forks are on a table nearby. The natural frequencies of the two tuning forks are 512 Hz and 384 Hz. They are silent before the string is plucked. Discuss whether you think either of the tuning forks will start to vibrate and why. The short answer is only the 512 Hz fork will vibrate or make a sound because it's an integer multiple of the fundamental frequency of the guitar string. If we want to look at that in a bit more detail, we might say that the guitar string will generate sound waves on the air, which will start to push on the tuning forks. The fundamental frequency of this is 256 Hz, but the guitar string also produces harmonics in multiples of that, so starting with 512 Hz. Which means if the tuning fork gets a sort of push from the sound waves, it might sort of start to do one oscillation. For the 512 Hz fork, the sound waves from the guitar are in sync with its natural oscillations. So they reinforce each other and you get resonance, whereas that doesn't happen for the 384 Hz tuning fork. So that one will not make any sound.